Okay, so we have two more opportunities for a +5. We have practice problems on Canvas. So I will show you. Okay, so under week 13, you'll see that I opened up two practice problems, protein separation, pH, and titrative acidity, which I'll cover today. So these are for +5. You can give me one next Friday and one the following Monday so that you time yourself and you submit them for extra credit. Again, they're not obligatory. You don't have to do them, but there are chances for extra credit. You get extra credit and you study at the same time for the final. So that it's good to do them if you have the time and if you're interested. Now, the other announcement I have is related to next week. So I have Plant Protein Innovation Center events Monday through Wednesday. So which means I won't be in lab and I won't be in lecture. So what's going to happen? Lab is going to go on like usual. Kat is leading. Nigel is your TA. Cindy will come and sub in case Kat needs help. So you'll be good there with the labs. On Monday, Samira, my postdoc, will come and give you a lecture on vitamins. It's a simple lecture. Usually it takes me half an hour to cover it, so we'll see how long it takes Samira. But here you'll see that I have posted last year's vitamin. It's the lecture I gave last year. So it's recorded by me, so you have it as a backup, but please come to lecture Monday. Samira will be lecturing. So Wednesday, lucky you, will canceling lecture. But the material that would have been covered on Wednesday, we have a recorded lecture, enzymes. So it's a very special recorded lecture. It's not me, it's the editor of Food Analysis book. So Dr. Suzanne Nielsen gave a guest lecture last year, and usually she comes every other year in person and give us a guest lecture, but due to COVID, she did it over Zoom. And she's retired, so she will never give any more guest lectures, but I have this forever as her guest lecture. So it's a treat. It will be on the final. It's a treat and a final. So please listen to it, but you don't have to be in class. So you have that lecture already for you. Okay, so I won't see you until next Friday. Lucky you, unless you are in the PPIC events. The last thing I want to point out, the student teaching rating. So the survey is open, and Laura created a +2 because we love giving you extra credit. I love to hear from you. It's very important that I get student feedback. I modify the class every year based on constructive evaluations from you guys. So please fill in the evaluation. And if you upload a picture proof that you have submitted it, you will get a +2. The assignment has been created and the due date is until December 20th, which is the final. But the sooner you do it, the better. Maybe before the final so that you don't hate me. No, just kidding. Just kidding. Anyway, so please do that. And what I'm going to do, let's see here. The last few slides from the proteins lecture, which talks about protein nutritional assessment and quality. I'm skipping for now. I just want to make sure we cover this for next week's lab. If I ever have time to get back to the last 5 slides, I will. Otherwise, it's okay. So we'll get going with that. All right. Let's try to remember what we know about organic acids, food or organic acids. They are weak acids, they have good buffering capacity, and they can buffer at multiple pH. What do you remember about organic acids? Nothing? Paige? So they are weak acids. They don't give up their hydrogen very easily. They have good buffering capacity. They buffer and resist change in pH. And can buffer at multiple pH. Why is that? It is correct, but why is it correct? Because organic acids might have multiple carboxyl groups. COOH, the one that gives you the hydrogen that makes them an acid. So different organic acids might have one carboxyl group, like acetic acid, for example. You might have two carboxyl groups, like malic acid, or you might have three carboxyl groups, like citric acid. So each carboxyl group has a specific dissociation factor. So that dissociation factor will give you a specific pKa. So that means when you have multiple carboxylic groups, you have multiple pKa's, you have multiple buffering zones, and we will talk about that in more detail. So that's what you want to remember for now, that all of the above is correct. The last one, number C, due to how many carboxyl groups your organic acid has. Let's think about this for a minute. You have two drinks, two solutions, two drinks, whatever they are. They have same pH. And I'm saying here, if they have the same pH, they have the same titratable acidity, but different sourness. Does this make sense to you? Michael?
False.
False. Yes, it is false. Because two different solutions or drinks might have the same pH, but might have different titratable acidity. And titratable acidity is the percentage of the total acid. So it is dependent, pH is dependent on how much free protons you have or dissociated protons you have. And the amount of dissociated protons is dependent on how strong or weak the acid is. So I'll clarify that when I give you an example here in a couple of slides. So let's differentiate titratable acidity versus pH. So titratable acidity, like I said, it's a measure of total acid concentration, and it is usually a percentage. So what's the percentage in your sample? What's the percentage of acid in your sample? So that means it's total acidity. It affects flavor, and it's an indication of maturity in some fruits, for example. So whereas pH is a measure of free hydrogen ion, or we call it either a proton or a hydronium ion. That's the name of it. H3O plus is the hydronium ion. And the more protons that are free, they're going to interact with water molecules to give you a hydronium ion. So the more hydronium ions you have, that will impact the pH. pH will be lower, and we'll talk about how the pH is calculated. So pH is a measure of the hydrogen ions that are free, the active protons, active acid. pH, what kind of reaction does pH impact in food? Ellie?
Forms acidity. example, I can think of is using like a single acting leavener and then you're adding acid to it, so like a baking powder, and then you're adding like acidic, like buttermilk. The pH of that would affect the reaction for baking.
Okay, so it impacts chemical reactions basically. Chemical reactions in food. What other than chemical reactions? Enzymatic reactions, thank you. Different enzymes have optimal pH at which they will be active. What else? One more thing. Not chemistry.
Biology?
Yeah, what biology? Yes, what are they?
Microbes?
Microbes, yes, absolutely. So the pH impacts the growth of microorganisms. So pH is relevant. So regardless of the concentration of the acid, the pH is what impacts our chemical reactions, what impacts growth of microbes, what impacts enzyme activity, not necessarily the total acid amount. Okay, so here's an example where titrative acidity and pH are not necessarily dependent on each other. So here's an example of hydrochloric acid at same concentration, 0.1 normal, and then acetic acid at 0.1 normal. So same concentration of the acid, same titrative acidity. However, hydrochloric acid is a very strong acid, so it will dissociate. That means it will give its protons out very easily. Okay, so it dissociates. So a 0.1 normal HCl has a pH of 1 at room temperature of 25 degrees C, whereas acetic acid is a very weak organic acid. It does not dissociate as readily as hydrochloric acid. So percent dissociation is very low. Therefore, the pH is about 3 compared to 1. So at the same titrative acidity, you have differences in pH dependent on the strength of your acid. One thing I point out here, we will mention it a lot, is conjugate base. So you have the acid, dissociated acid, and this, the negative charge component is called conjugate base. So this is a term that will come up later. Okay, so basically, the pH is a spectrum of acidic to neutral to basic. So acid is a proton donor. That means it gives out its hydrogen and forms hydronium ion. Base is a proton acceptor and forms hydroxide, an OH minus. So at neutralization, which will be important for us when we determine titrative acidity, is always we titrate with the base to determine titrative acidity. Acid plus base gives you a salt and water. So basically, the proton will react with the water to give you a hydronium ion, and then the bases are represented by a hydroxyl group. So there is the ion product constant for water, which just from it stems the pH. Is the ion constant, product constant for water at 25 degrees C is about 1 times 10 to the negative 14, sorry. So the 14 is the range of the pH from 1 to 14. So basically here at pH 7, hydronium ions concentration is 1 times 10 to the negative 7. And the hydroxyl group concentration is again 1 times 10 to the negative 7. So this multiplied by that gives you the 10 to the negative 14, which is the ion product constant of water. One thing you need to remember is the pH is negative log or inverse log hydronium ion. There is POH too. It would be pH for acid, POH for the hydroxyl. But don't worry about pOH. pH is what we normally refer to. And if you have a concentration of 10 to the negative 7, the negative log of 10 to the negative 7 is 7. So let's do a series of calculations. Pull up a piece of paper. Again, 4 plus 2. All these plus 2, for those of you that need participation, this will count towards that. Okay, so here we want you to practice your calculator and the log. Every calculator is different. I'm old school with all types of calculator. So you just want to know how to use the log and inverse log on your calculator. Okay, yeah, first of all, if you have 3.55 times 10 to the negative 4 concentration of hydronium ion, what would be the concentration of the hydroxyl? You just want to apply that always you have a product of 1 times 10 to the negative 14. You want to assume a temperature of 1.5. So always this is the product. So you have X, you solve for Y. X times Y equals the product. And then you calculate the pH based on the concentration of the hydronium. Once you have values, let me. You have a value for both? Okay, go ahead. Tell me what's the concentration of OH.
I have 2.82.
Correct. And what is your pH now?
3.4.
Correct. So you can take a picture of that if you want, unless you figured it out yourself. I'll give you a minute to do that. Ready to move on? Okay. All right, so beer has a pH of 4.3. Now you have the pH. What would be the concentration of the hydronium ion? That's where you want it. That's again exercise for you to learn how to use your log function on your computer, on your calculator. Learn or remember. You got it, Shri?
Yeah. I got 5.01 times 10 to the 5.
5.01 times 10 to the negative 5? Correct, okay. So there are different ways. This is my old school solving it, but you might have a direct function that will give it to you. So again, you just want to remember to use this equation. And it's just a matter of how you use your log function on your calculator. Okay. I'll wait for a couple of you taking notes. Good? All right. So very quickly, the pH meter, you're going to be using the pH meter in lab. There's a lot about the pH meter in the textbook. I don't expect you to know the details there. It's just what is a pH meter is a potentiometer, basically, because it measures the active hydrogen ions, measures the activity of the hydrogen ions versus the concentration. And there is a link between activity and concentration. We're using a constant, which is the activity coefficient, that is directly related to the acidic or the strength of the acid. Now, what does the pH meter measure? It measures voltage. So it measures a change in the current based on the concentration of the hydronium ion. So the concentration of the hydronium ion is proportional to that change in electrical current. But it is really very, very small change. It's not like you don't have a huge potential going on. So that's the word infinitesimal. I mean, very, very small current measurement. So in your pH meter, you usually have a reference electrode, and you have an indicator electrode, and you have the voltmeter that measures the change in the potential order. So the reference electrode keeps everything like stable at a specific current, and then the indicator electrode measures a change in the current based on what you have in your solution. So the reference electrode always have a solution in it that keeps a constant reading. And then when the indicator electrode detect a change in the potential, that would be proportional to the concentration of hydronium ions or the active hydrogen, which gets converted to pH. All right, so in the past, all pH meter used to have the reference and the indicator electrode separate, but now they're both in together, put together, combined. And it's made up of either glass or plastic or whatever. So you will see that you only have one electrode that contains both the reference and the detector or the indicator electrode for your pH meter. You already used the pH meter in lab 3, so this will be a refresher for using pH meter. And actually, are they going to calibrate themselves? Yeah. So you will learn how to calibrate the pH meter, which is a good thing to learn. And usually we calibrate using 2 different buffers that have a 3 pH in it difference. So either pH 4 and 7 or pH 7 and 10 will be used for calibration to do a 2-point calibration. We always need proper maintenance of the pH meter. You want to make sure that you have your reference electrode is not dried, it has the proper solution in it. Your electrode is not dirty. So let's say in our lab, we measure a lot protein solutions. So protein can potentially stay on the glass or the plastic. So we want to make sure that we wash that off or clean that up. Oftentimes we need to use digestive enzyme like pepsin or trypsin or something to put the electrode in an enzyme solution to basically break down the protein sediment on the electrode. If you are measuring pH in a sample that is high in fat, so again, you want to wash that fat off, and usually we use a methyl alcohol or something, methanol or something. Otherwise, general cleaning is with dilute acid. So like a 0.1 normal HCl, you can do general cleaning. So the pH meter comes with instruction for proper maintenance. You also instruction for calibration and proper storage with the reference buffer that you need to make sure that your electrode doesn't get dried up. Titratable acidity. So what is titratable acidity? It is a measure of the concentration of the acid that is native to the food or added to the food or beverage. And to measure acid, it's simple. It's titration with a base. So last week or this week, you did free fatty acid. So basically, you just titrated against NOH. So that's what you will be doing in the lab for different beverages. You have your acid solution, and then in your burette, you would have your NOH, and you basically titrate to equilibrium. Different organic acids in different beverages or food could be citric, malic, lactic, tartaric, acidic. So these are organic acids. There's so many. Citric acid is common in orange juice, lemon juice, 7-Up. Malic acid is from apple, lactic acid would be in dairy product, tartaric in grapes, and so on. Inorganic acids, often used, is phosphoric acid, often used in beverages. And carbonic acid is something that is formed when you have CO2, when you have fizzy drink, so you have CO2 in there. CO2 with water forms carbonic acid. So it reduces the pH of your beverage. So when you titrate to reach endpoint, we determine endpoint either by using an indicator. In this case, we use phenolphthalein indicator, and or we use a pH meter to determine endpoint. So by measuring the pH, we know when to stop the titration. So let's talk a little bit about titratable acidity, considering the buffering capacity of the acids. So we talked about buffers earlier in the semester. So the Henderson-Hasselbalch equations come back here. So what happens is, why do these organic acids buffer? They buffer because in the presence of water, the acid partially dissociate. So you end up having salts or conjugate base and acid, non-dissociated acid at the same time. So what does that mean? When you have conjugate base, that means dissociated versus non-dissociated, HA, having the proton. So you have the dissociated and non-dissociated together, present at the same time. So meaning, why do they act as buffer? Because when you, let's say, titrate with NOH, so you're adding OH minus. So the non-dissociated acid is going to give a proton and neutralize the OH minus. Then the pH goes back to where it was. If we are titrating with an acid, the A minus, the conjugate base or the salt, is going to pick up the proton from the acid we titrate and again resist decrease in pH. So that's why the organic acid buffer, because it has the negative, dissociated, and the non-dissociated. So it either picks up a proton or gives up a proton, depending on the changes in the environment. So that's why it kind of buffers the pH. So the Henderson-Hasselbalch equation brings back memories from the buffers lecture. So pH equals pKa log plus log conjugate base over non-dissociated acid. So maximum buffering capacity occurs when pH equals pKa. Why? Because when you have equal concentration of conjugate base and non-dissociated acid, log 1 is 0. Then pH equals pKa. You have maximum buffering capacity when the concentration of conjugate base equals the concentration of non-dissociated acid. Why is that important? You'll see that the acid containing different carboxyl groups, they would have different pKa's, either one pKa if you have one carboxyl group, or two pKa's if you have two carboxyl groups, or three pKa's if you have three carboxyl groups. This means that that acid buffers at three different pHs, because each carboxyl group have a different dissociation factor. So basically, this is important when we plot titration curves. When we plot titration curves, what is a titration curve? Titration curve is when you're titrating with a base, so here you have NaOH. And, here you have the pH. pH, and here you have volume of NaOH. So when you're titrating, you expect, when you're adding NaOH, you expect the pH to go up. But you'll see something like that. Let's say you have malic acid, which will be your apple juice will have malic acid. So malic acid has two carboxyl groups. I don't remember what it is, 3 point something and 5 point something. I don't remember the pKa actually. So you'll see around the first pKa, you see that no matter how much you add, you have very slight change in the pH because it's buffering, maximum buffering capacity. And then the second carboxyl group has a pKa of around 5, let's say. Then again, around that time, that pH, you have maximum buffering capacity. You're adding NaOH, but it's not changing the pH. And then after, we see a sharp increase in pH. Why? Because as you're titrating with NaOH, you're giving up protons. Titrate more, you're giving up protons. All of a sudden, you are depleted, or you have very little amount of non-conjugated, or you have very little amount of acid, non-conjugated, or non-dissociated, acid. When you have very little amount here, then the log value increases dramatically, the pH increases. So when this starts to get close to 0, then you see a sharp increase in pH. And hence you see a titration curve similar to that. Suddenly your pH goes up because you're running out of non-dissociated acid. So in titratable acidity, you want to reach an equivalence point. That means the end point. When all of the acid has been neutralized by the base during titration. At that point, number of acid equivalents equal number of base equivalents. Okay, equivalence of acid equals equivalence of base at neutralization point. And that's when we see a rapid increase in pH is noted. That's when we depleted all of our non-dissociated acids. So here are different titration curves for different acids. So this one here is for HCl. HCl, you don't have, it's not a buffer. So there's no pKa buffering zone. So with HCl, it's a very strong acid. All of the protons are dissociated. Then you see a very increase, gradual increase or linear increase, and then the sudden change in pH. Whereas here, if you have acetic acid, one carboxyl group, it has a pKa of 4.75. So you see here an increase, and then kind of a plateau or very minimal change in pH, and then increase, and then your point of equivalence, sharp increase in in pH. Citric acid, you have 3 carboxyl groups, 1, 2, 3. So you have 3 pKa values, 1 for each carboxyl group. So you see a linear increase, a plateau like a ladder. So you plateau here, a little bit of increase, plateau at the second pKa, increase, and then plateau at the second, third. And when all of your non-dissociated acids are depleted, you see a sharp increase, and basically neutralization is halfway here. Usually the midpoint at pH 8.2 is neutralization. Now, I'll ask you later why it's pH 8.2, not 7. But keep that in mind, and let's do this calculation here. At pH, on that same sheet of paper, at pH 4.7, what percentage of lactic acid is dissociated and present as the conjugate base? pKa of lactic acid is 3.86. So here I gave you the pKa and I gave you the pH, and I'm asking for concentration, percent concentration of conjugate base. So your Henderson-Hasselbalch equation is pH equal pKa plus log of conjugate base over not dissociated acid. So percent, so the 100% then equal concentration of A minus plus concentration of HA. Or 1 equal also A minus plus concentration of HA, either or. So just substitute HA in the equation as 1 minus A minus or 100 minus A minus, whatever you want, then you would solve for A minus concentration. So do that and tell me what you find out. Anybody with an answer? Do you have an answer, Michael? What? What's that? Say that again.
I
87%, correct. Yes. So it's just, again, a practice for you to utilize your function, log function on your calculator, solving for A minus. And if you use 1, you'll get 0.87, and then that translates to 87%. Take a picture of it, right? Okay. Good. All right. So once we have this rapid increase in pH, we reach the endpoint, and we can use a pH meter to determine that. But with pH meter, the response is really slow. Sometimes you're titrating and the pH meter takes few seconds to adjust and equilibrate and give you a reading. So you might overshoot if you're not careful. So you really have to be very patient if using a pH meter to detect the endpoint. You have to have like few drops, wait, and then towards the end, when you know that you're getting a color and it's fading, then you go slowly, drop by drop, and let the pH pick up and give you a reading. But oftentimes we use an indicator, and specifically phenolphthalein indicator, it changes color from clear to red in the range of pH 8 to pH 9.6. So once we reach pH 8 or 8.2, the neutralization pH, we see the pink color. So that's when we know that this is the end of the reaction. So why is the end point 8.2 and not 7? So point of neutralization is usually 7, but in reality, it's 8.2. So when you think neutralization, you're going to think neutral pH. You're going to say pH 7. But in reality, the end point is at pH 8.2. Any guesses why? Shri? Say that again.
They're weak acids.
I can't hear that.
Is it because they're weak acids?
Weak acid, so there is a presence of conjugate base. That's the answer. So yes, because they're weak acids, we have the A minus, the conjugate base. It kind of raises the pH. The presence of conjugate base raises the pH. So the actual point of neutralization, the pH is at around 8.2, which is in the range of the changing color for the indicator. So that's why if we're using a pH meter, your endpoint is pH 8.2. Now, but we have a problem when we have phosphoric acid in here. Phosphoric acid and carbonic acid, they buffer at this pH. So when you're titrating, if you're titrating to try to determine phosphoric acid, it's not going to work out with the phenolphthalein indicator because it's going to resist the pH change and you won't see that red color change. So it's really hard in this case. So when we're dealing with acids that actually buffer around this pH, so you don't see that change from clear to red, we use a pH meter and we just stop when we reach a pH of 8.2. Now, if you are trying to get the titrative acidity in a beverage that is dark in color, like tomato beverage or something like grape juice or whatever, so you won't be able to see. We always use a pH meter and don't use the indicator. You won't be able to see the change in color. Okay, what you're going to do in the lab, you're going to use a carbon dioxide free water. Why? Because we have an issue with carbon dioxide in your, if you have carbon dioxide in water or in your sample, like you are trying to get the titratable acidity of 7-Up, we have to boil off carbon dioxide because carbon dioxide will form carbonic acid with water. And carbonic acid, we said, is going to buffer around pH 8.2. So you don't want carbonic acid. So what you're going to do is in lab, you're going to boil off carbon dioxide from a fizzy drink, and you're going to use carbon-free water, carbon dioxide-free water. when you're doing the dilution and everything. So you don't want to incorporate any carbon dioxide. That is from one end. From another end, you're going to standardize your sodium hydroxide that you're going to use for titration. That means you want to standardize it to determine the exact normality of your base so that you can use it in the calculation to get accurate titrated acidity. Why do you want to standardize your NaOH? Because over time, when your NaOH is stored, prepared and stored, there will be a CO2 that might be dissolved in the solution or the reagent, and the CO2 is going to react to give you sodium carbonate, which will precipitate and will change the concentration of your NaOH. So over time, really, you want to either prepare fresh NaOH, or when you prepare it, you want to make sure you calculate the exact concentration for any potential of production of sodium carbonate. So, and also when you are weighing out NaOH, diluting it to prepare your 0.1 normal, you want to account for any dilution error. So standardization is important to also account for any preparation or dilution error. So you know exactly what your normality is. So what we do in the lab when we boil off water, what we do is we attach something called ascaric trap. So you'll see an ascaric trap, which is basically silica coated with NaOH. And we attach it via tube to a flask that has the water. The flask is sealed, and then there is like an arm to the flask that we attach to the tube. You see it in the lab. So any CO2 that remains in the headspace will be taken up by the ascaric trap, because it has a layer of NaOH. The CO2 will react with the NaOH. So basically, the NaOH traps the carbon dioxide, making sure that the water that you're using has no dissolved CO2 to avoid any carbonic acid in your sample. So you're going to standardize NaOH against the standard acid, which is potassium hydrogen phthalate, or potassium acid phthalate, can be called the same. It's the same thing. So it's a standard acid. You will use it to standardize your NaOH. So there is a procedure that you will follow in the lab to standardize and calculate the actual normality of your NaOH solution prior to titration of your sample. So calculation, this is, I'm going to keep you for a couple of minutes to finish this. The calculations here, basically the same neutralization equation that you've been using in the past, that you used it for fatty acid determination and other equilibrium equations. So basically normality times volume of the base, molecular weight over the weight of the sample, but you will have a volume next week instead of the weight, so it will be a percentage volume by volume instead of weight by weight. And then, weight by volume instead of weight by weight. And it's a percentage, you multiply by 100, you divide by 1,000 because the volume is going to be milliliters, so you're converting. Now, one thing here is different. Instead of molecular weight, we're going to use equivalence weight. Why is that? You have to think about your reaction and what is transferring in the reaction. Protons are being transferred in the reaction. So if you have 2 or more carboxyl groups, your equivalent number will not be 1. So if you have 2 carboxyl groups, your equivalent number is 2. If you have 3 carboxyl groups, your equivalence number is 3. So equivalent weight is the molecular weight divided by the number of equivalents. So depending on how many carboxyl groups you have. So in lab next week, for 7-Up, you have citric acid. So it's 3 carboxyl group. So The equivalent weight is the molecular weight of citric acid divided by 3. If you have 3 hydrogens that are being transferred in the chemical reaction. Now, if you have malic acid for your apple juice, that will be the molecular weight of malic acid divided by 2. You have 2 hydrogen, 2 carboxyl groups that are participating in the equilibrium reaction. Okay, so that's the only difference for titratable acidity than any other equilibrium equation is when you have more than 1 proton being transferred in the reaction. So you have to account for equivalent weight, not just molecular weight. Okay, and the explanation is kind of here for you. Okay, so practice this on your own. You should, yeah, and you can practice it and give me your sheet next week with the answer to this. It's just basically making note that citric acid here has 3 carboxyl groups. The molecular weight is divided by 3. Okay, so that's the, and then you apply the equation. Basically, add it to your sheet of paper and give it to me next week. And then the last thing I want, just before the last thing, this is showing you that in fruits or foods, usually percent acid is very low. It's hardly above 1. In very rare occasions, it's above 1%. So in an exam, if I ask you to give an estimated number for percent titratable acidity, don't say 20%. It's not there. One last thing, so titratable acidity is usually calculated based on the predominant acid. There might be multiple organic acids, but you use the predominant acid in your equation. It's predictor of acid flavor by getting the bricks related to the sugar content, the acid ratio, and quality indicator for wine specifically. So if you have acidic acid in wine, that's not desirable. So you measure titratable acidity of wine, then you boil the wine. So acidic acid is volatile. So acidic acid will evaporate, then you do titratable acidity again. There.
So when you hear like these products referring to low acid, would that be enough?
Say that I didn't get any.
So it's like a food referring to like low acid, would that be in reference to the pH and type 3 fluids, or like how would you determine that for like the can product?
So if you want to determine acidity of a canned product, so you do 2 things. You get the pH of it and you get total acid. So you need 2 values. The pH tells you the actual pH of it that impacts reactions and impacts microbial growth. And then the total acid tells you how much acid you have in your sample. The 2 measures. Okay. Thank you guys. I will see you next week.
Do we need to know the stuff we didn't cover from the rest of that?
If I don't get it, it's next week. Oh yeah, I'll take it. Is this characterization? No, protein. Okay, got it. Oh, did you solve the last one?
No.
Solve the last one. I'll take it from the next week. Why are you giving me mine?
Practice problem.